Let's move to our final topic in this chapter, which is the shear stresses in the thin wall sections. Previously, we considered the change of shear stress along the radius or the distance from the centroid of the cross-section. We draw a conclusion that tau varies directly to the distance from the centroid of the circular cross-section. However, in the thin wall sections, we assume the tau is a constant. To do this, we will introduce the Bugert-Bethel theory. Excuse my pronunciation. Before we derive our formula, let's discuss about our assumptions. First, the cross-section should be a closed cross-section. Besides, we assume the thickness of the cross-section is very thin, such that there is no change of shear stress across the thickness. Now, we draw a differential piece of material from this closed cross-section and take the force equilibrium. Then, by considering those two forces, we know that tau1 T1 dz equals to tau2 T2 dz. By cancelling the dz out, then we have tau1 T1 equals to tau2 T2 equals to Q. It is an important quantity in solid mechanics called the shear flow. The theory is derived by considering the differential torque dt equals to QR ds. Consider a piece of material under the shear flow Q with the length ds. Since for the shear flow, it has already taken the thickness of the material into the consideration, then Q ds is just a force, a differential force acting on this differential element. Therefore, we can write the differential torque equals to the differential force times the arm, the length of the arm, r. As what we derived, Q is a constant, it is uniform. Besides, we consider the area of this very small triangle swiped by r. For this very tiny piece of triangle, this is ds, and its height is r. Then the area of this differential region is given by dA equals to r ds divided by 2, according to the triangle area formula. Therefore, since Q is a constant, it can be taken out from the integral. Therefore, we can write T equals to Q times the circular integral of r ds over the entire length of S. Since dA equals to r ds divided by 2, we can find the area enclosed by the center line of the thin wall structure. The area is given by 1/2 of the circular integral of r ds over S. Consequently, this item will then become 2a. Therefore, T equals to Q times 2a implies that Q equals to T divided by 2a. Since Q is a constant, which is the shear stress times the thickness, we conclude that the shear stress in the thin wall section is given by tau equals to T divided by 2AT. Here are some examples of the calculation of shear stress inside this thin wall section. First, for the circle, area equals to pi r squared, and since it has a uniform thickness, then T is just T. For this rectangular section, A equals to BH. So this is A, this is A. However, the thickness in this thin wall section is not uniform. The thickness here is T1, while the thickness here is T2. T2 is greater than T1. However, we can still calculate the shear stress inside this thin wall cross section. You replace T by T1 and T2 respectively to find the shear stress inside each member.